Okay. Thanks, Rifki. Okay, so you send me email.
Oh yeah.
You want to do something more related to your research topic?
Because me and Zach thought like many of the topics are kind of intersecting. So since the other week you mentioned, oh guys, if you're interested, we can do camera calibration. We thought if there is anything that you can fit in the course that could be interesting, we'd be happy, of course, to
I actually thought I did that because the
yes,
optical flow part is
yeah.
exactly what you want to work on,
exactly,
right?
yeah, the optical flow.
So
Also the contour detection was interesting for Zach, for example. So
Yeah.
definitely. Without knowing our topics, use it.
So I think that's okay. Zach isn't here today,
I
though.
think he's coming.
Is he? Okay.
I think yes.
Then we'll give him another couple of minutes.
Yeah, because the course officially starts at 9 or 9:30.
9. I thought it said 9.
Because I think it's 9:20, so maybe I think that's why.
Okay. Anyway, no problem. Well, then in the meantime, we have a new TEEP student here, Parik from India, so you can introduce yourself quickly. He's going to stay 3 months here.
Hello everybody, my name is Rifki and I'm from India. I'm here for an internship of 3.5 months, working with Zaki on the robotics topic. So I can gain experience and gain knowledge about robotics.
And your background in programming?
Like I work on robotics, like on robot software, robots. In programming, I know Python. I know which to operate OpenCV. Like I know the mechanisms and know to design the things, like design.
Okay. And hobbies? That's what I asked all of them when they started the class.
Hobby is playing badminton.
Badminton, okay. Cool. I think we have badminton courts here at NTNU in the...
I think it's at the sports center.
Oh. Good. Then also for all the students, about the assignment, first assignment, arrange a time with Rifki to demonstrate your assignment. That can be done, since this one is a pretty simple assignment, that can be done in person or virtual. Meeting.
So we text him over Discord.
Text him via Discord and then just say what time you want to do the demo. And you too, you guys, right? You also have to send a message to Rifki asking him to demonstrate the assignment. To demonstrate your assignment 1, connect the dots. Okay, good. Then what I want to do today is to work on my problem. think they're just switching over the server, they said. And like everywhere else in the world, the web pages become bigger and bigger and longer to download. All I want is the marathon rules. Right, so your colleague sent me an email asking if we can do something that fits more closely with your master's thesis, PhD, graduate thesis work, which is okay with me in principle, as long as it's something interesting. We certainly won't be working exactly on your master's topic, but we can certainly discuss some of the technique and approaches that will be available. So for you, you're doing Visual Slam,
Yeah.
right? I actually included the optical flow for that, so that will serve you well, I believe. But I don't know about your project. What is your project?
Object detection.
But I mean, what kind of objects?
Basically, human detection using borders and stuff, edges and stuff.
Okay. If he says what?
The purpose of the system, like to censor nudity online.
Oh, okay.
On social media and everything, so this is the kind of intended purpose.
Yeah. That was a huge research topic in New Zealand. All the students wanted to do that because at that time when I was at the University of Auckland, the internet costs for New Zealand were horrendous. So basically every student only had about 10 megabyte quota per day.
Oh, wow.
So if they could get a project like censoring anything, right? And nudity was a popular one, then they could get a lot more internet quota, and then it would all be part of their research, right? So then they all came up. Pretty much every fifth student that wanted to do a master's thesis came and he said they were all very concerned about nudity online.
I'm very concerned.
Yes, yeah. You're a real Puritan, right?
Yes.
Yeah, so there have been projects that have been going on for a long time, and it's not my research area, but sort of listening to the conferences at that time, one of the things that is surprising is that for at the beginning of the course, we talked about color models and color predicates and everything, right? And color turns out to be very, very difficult as a feature, right? But skin color is actually relatively easy. Like for some reason, skin is not too bad. We had one project with students of mine, which I admit I was a young, naive professor, so I probably wouldn't do the same project nowadays in this political climate. But we found an old robot arm in the dumpster somewhere, and then we refurbished it, made it work again, and then we wanted to show our color camera calibration in 3D, right? And then first I actually wanted to play badminton, but the robot arm wasn't nearly fast enough to do a good job with that. So then we bought one of those little toy Nerf guns and put those in the hand of the robot, and then the robot can actually track and shoot you, right? With the little rubber bullet, of course, like not a real bullet, like the Nerf arrow, right? But my students thought this was hilarious. So the cleaning staff, when the cleaning staff came in, the students kept the system running. It didn't shoot, right? But it tracked the person with the little toy gun. But even that is intimidating, I have to admit, right? It's not, yeah, and so yeah. So then we had to obviously apologize, and I had to go to the dean and everything.
Oh, with the
Yeah, yeah, yeah.
That's serious.
It's okay. They didn't fire me, so. It wasn't. I mean, yeah, we basically said it was a mistake. We didn't want to run the system, but students forgot to turn it off and everything. But admittedly, 3 months later, we had a break-in in the lab, and somebody stole our laptop. So maybe if we had that gun running still, then maybe my laptop would still be there, right?
It was in New Zealand.
Yeah. So anyway, that's one thing. And the other thing that even in the mid-90s, the pornographic detectors worked quite well, right? Because a lot of the pictures are quite crass and stereotypical. The only problem they had were deserts. The desert has sort of a skin tone, pictures of the desert, and the curves are sort of similar as well. So one of the biggest problems that they had for false positives were desert scenes, like these kind of images.
Oh, like that.
That's a very specific example, and you said this is not your
Yeah,
research area. Wow.
Because of the curves and the.
Yeah. So this kind of image would trigger the systems in the 90s. Nowadays, I'm sure we can do better than that. In fact, we can talk about. Yeah. Okay. Okay. So, I mean, for pose recognition, the deep learning approaches are at the moment the state of the art. I think there is other approaches that would also work well. However, deep learning sort of gets a huge boost because it runs efficiently on a GPU. So they sort of won the lottery as far as hardware support and hardware speed is concerned, right? And that would definitely be a viable possibility. I'm sure somebody must have done that already, run like 1 million images with pornography, without pornography, through a deep learning architecture, and then just use that, right? If you don't want to use that, then we need to. But why did you say you were interested in object tracking? For that particular application, it would just be object detection, right?
Because like I'm not just focusing on nudity. It could be other instruments as well that involve sexual stimulation.
Okay. Okay.
Scene maybe. I was hoping, because my knee-jerk reaction is do deep learning, which I'm pretty sure everyone has already.
Yeah.
Before.
I mean, that's what my students would definitely do. The first thing they would do is just run it on the GPU and.
So I was thinking, is there a more faster way instead of like doing the typical training that you just label them or not or.
Well, see, that's why I don't like to do the deep learning. I mean, I have, for a lot of labs nowadays, one of the professors here in Taiwan, I won't mention the name, but he basically said any new graduate student, the first thing he has to do in his lab is label 3,000 images. Because that's all you do, right? Then, on bounding boxes and things like that, right? And I certainly don't want to do that. I don't even want my students to do that. So we would look at trying to find ways to be a lot more economical with our training data. Now, let's think about that. But yeah. Okay, but this is related to your work, but we're going to do it in the Fiera robot domain because that's a lot safer and also relevant for us because next week, Saturday, Sunday, we have the competition in Kaohsiung, so at that point the system has to run.
So we'll be meeting next Monday.
Pardon?
We'll still meet on Monday next week.
Yeah, sure. It's not the coming weekend, it's 20th, 21.
Okay.
And also make sure you join the class today, at least at the beginning with the German students, because we have that again too. Okay, so then I'm actually at the right page. So we talked about the Fiera Eurocup competition for humanoid robots. Today we're going to look into approaches for helping us in the marathon competition. The marathon competition started out very simple, like a line tracker, and if you see the track outside, the door there, that's my students working on the marathon for Fiera. So initially the robot had to track a line on the ground, but nowadays the second part of the track is not a tape anymore, but it's these markers. So there's a marker here, go forward, then turn left, then keep going straight, that kind of thing. So the robot needs to identify the markers, and it actually has to do a bunch of things, but before it can do any of them, definitely it has to be able to identify the markers. It needs to align with the marker as well, so that if the arrow goes straight and it points this way, then it has to know that it has to go here first and then turn and follow the marker, instead of just cutting the corner, which may move it too far away from the marker to see the next one. So there's some issues with respect to the path planning and things like that, but of course before we can do anything in this particular domain, we have to detect and identify the markers. So here we have the straight marker, and here's one for going right, and here's one for going left. And when they're on the floor outside there, you can see then you have reflections, noise in the image. There may be occlusion with another robot that sits in front of our robot. And it's kind of an interesting trade-off, because if you want to walk very fast for the marathon, which of course is the whole point, right? Actually, the main point is energy efficiency, but you want to walk as quickly as you can, given the amount of power that you have for the track. Then you need to look ahead, right? But that makes the vision problem harder. If you look straight down, so now this year my students, they have implemented where our camera is actually looking much more downwards than it usually does. And that makes our vision problem a little bit easier. Now, let me take screenshots of those 3 markers. And then we're going to start talking about algorithms for trying to detect those. Detect and identify those. Can I name this still? No. Okay. So this was marker left, right? Yeah. Okay. Then not here. Marker right. Okay. And the straight marker. Here we have the straight marker. So given these three markers, now they're on the ground. I know we can calibrate the cameras. So that would be okay. I'll get them to roughly that size. The size may be a little bit bigger, a little bit smaller, but it won't be that much difference. And then what do I do? How do I identify the markers? Any ideas from you guys? How do you identify the markers?
Like, when we mean identify the markers, like, the robot knows whether it's left, right?
No, the robot has to know, is it left, right, or
so it's automatic.
straight?
And my brute force idea would be to run corner detection, and then I count, like, if on the left side of the picture I have this number of corners, it's left. Because the other is more complex. But this is very brute force. There's a way to be better. Like if I see a certain amount of corners on the right, I know it's right.
Okay, then that's not a bad idea, right? And how do you do straight?
Yeah, straight, the top part of the picture needs to have 1, 2, 3, 4, around 5. Or, yeah, that's how we go about it. But I think there's must be a better way.
No, but that is not a bad idea. Certainly something worth trying. So implement that for the next 15 minutes or 20 minutes. Okay, so download the images and then run it through OpenCV, the Sobel Edge detector. And then your algorithm was basically calculate the number of corner points in the different parts of the image. And you can use the Google Collaboratory or your local Python installation. This is actually pretty similar to what my students are doing at the moment.
When we mean corner points, are those like those 3 endpoints of the triangle?
I think that's the idea, yeah. But if you apply the corner detector, then I think you will also get these points here. And actually Benson, the student that implemented this marathon marker identifying algorithm, he did say that one of the problems they had was if there's too much noise in the image, the algorithm wouldn't detect those short lines here. So he's actually running more than a corner detector, he's actually running a line detection algorithm on there. But that you can do using the Huff lines. So if you want to try out line detection, you can do that as well. Now, of course, first, I guess you can try it on the perfect image, right? If it doesn't work on here, then
It's not worth
it's not worth trying to do it any other way, right? But then you want to also try it with the image distorted by noise. And I will do my version on the collaboratory. Move that. Come on. Hmm. Okay, move that. Yeah. Courses. No, 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 no. we don't need this. Oh, how come you're looking for checkerboard? The corner, yes. Okay. So you can. There's various corner detectors built into OpenCV. You can use the Harris corner detector or good features to track, which is the one that we used, and then shoot from classic. So there's a couple of options. So then I'll try and get those images. Marker left is equal to add the image. Marker left. URL is equal to this. Suffix is equal to PNG. Marker left 00. Marker right is here. And marker straight. Will be here. So 3 columns, first image. Open. So take that. As array as numpy. So the resize should be image marker left dot width divided by 2 and height divided by 2. Okay, so now we have 175 pixels approximately across, right? Now I want to do that create an image with an image and a size, a factor. here we have that. Ah. So here are my three images loaded up, just so that I can actually have a look at them. And here I'm going to make that into a slide. So our first idea was run a corner detector on the image, and then next thing we have to do is threshold it, I assume, right? So threshold and then count the number in the different quadrants. Actually, let me show it like this. So let's see how that works. So which corner detector did you use?
Good features to try.
Yeah, okay. Then I use Harris.
Try Harrison, good feature.
Ah, okay.
So
Yeah.
it's the same.
The output should be pretty similar, right? Is that what you found?
I'm just looking at the difference, like which one is better.
Okay. Let me see.
Harris looks like this.
Mm-hmm.
So basically, that's the
Oh,
choice.
that's kind of like perfect.
I mean, it's a really quick. Although it did see the lines of that. Okay. Or should it be like?
No. The lines are fine, and the dots that you found. I think the lines is what you're drawing. How do you draw it? Do you scatter or plot?
I just use plot.
Plot. Then plot draws the line.
Oh, I see.
If you don't want the lines in
It gets
between,
scattered.
then you have to use the scatter plot.
Uh,
But in this case,
I mean,
it works.
It works.
They even came out in the right order for you.
although, what's the next? Because I'm thinking, like, if I like, will this have to count the number of points in, like, is it each quadrant?
Yeah. Then, given that this is a small shape,
So we're gonna
the
divide
simplest one would be to calculate the number of corner points.
And which one has the most points? That's most likely to be the like this one.
That's not what. So let me just get that same image, and then we can discuss it. I'll just use the Harris corner detector,
Okay.
simply so that we'll use a different one. So get the corner points from an image, and probably some parameters I need later on. I'll add those later. Then gray is image, and like I said, I'm usually just lazy. I'll just pick the green channel to do the conversion. That runs then a little bit faster. So I don't want to overwrite the image. You could actually do that, but I'm gonna create a new image. And that will be mp dot mp dot zeros image dot shape. Excuse me. Two, 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 and then ax4 is equal to fig dot add subplot 2, 3, 4 ax4 dot im show corners left. Here 12, 4. Hmm. Four. Okay. So this one has an alpha channel, so I think I need to put extra 0 here. Extra 255 here. Okay, actually I could have just painted it over this original image, but okay. Corners left, then corner right. Straight, straight. This would be true 6, 5. So this is the output that I get by just running the corner detection on the images, on the 3 marker images, right? And it's sort of a best case. I use a pretty standard parameters for the Harris corner detector, and then when I do the thresholding, I use the maximum response from the Harris corner detector as sort of a guide. So if you look at the actual thresholding that I'm doing here, then any pixel where the response of the Harris corner detector is greater than 50% of the maximum response that I got in this image, I will paint it as blue, I thought. No. Reddish. And with some transparency. So if I make that 0, yeah, and then bluish. Now I can play with my, as you saw, 50%, which was the value that I guessed at, right? That didn't work for this image here. The center one, it missed a couple of points. So then I dropped it to 30%, and now we get like a perfect response for our corner points. Now I could do that to try and match a template or any other kind of algorithm that I want to suggest. Now, your idea was to take that image now and break it down into individual components, quadrants, and then calculate the number of corner points in each quadrant.
Yeah,
right?
it's kind of working.
Yeah. But if it's kind of working for these images, then it's going to be very hard to make it work in the real world, right? So that approach is
I think this is really good for, like, I've calculated the number of points it detects on the bottom, top, left, and right, and now I'm just doing if this situation is left, if this is right. And I mean, I got this input picture,
Right,
and my guess is right.
Yeah.
And he's right. So if I do it and get another picture, for example, I will right again. And now we're supposed to do the idea.
Yeah. If we have that perfect input, then it's going to work. So it's not a bad idea. However, realistically, if we look at the image from the robot, then what are the big? So the first problem is that it's going to be very hard to register that image so that you get exactly the pixel coordinates that you want, right? So we want to simulate that. Now, one approach that you could pursue and that will work, but is quite labor intensive, I think, would be to take a lot and lots of images from your robot, right? So, and in a sense, that's kind of the best thing you can do. And if we had a robot here, we could do that. But I don't have a robot here right now. I also don't want to spend so much time to work on those images and label them and capture them.
We can try something like it's going to take like less than 5 minutes. If we want to train a model to do that, we can do it with teachable machines.
What? Teachable machines. Yeah.
Yeah. So like left, and what I do sometimes just with webcam, and I take plenty of pictures of the left, and then right just and work.
Yeah.
Just,
that works. Yes. We also have our vision pipeline set up. Still, you need to have some input images. Now,
you mean printed?
not printed, but yeah, you would need to print them if you want to take an image. Yeah. But I think one thing that is clear is that if we know we're not going to be able to register the image accurately, then probably we should take that into consideration. So before we run the algorithm now, what I want to do is first I finish my classifier, and I'm just going to have it print out whatever it detects, right? But then we want to try that on several images that are not so perfect. And the one thing is not to take real images that are never perfect, or we can use the idea of image augmentation, and we can introduce the kind of errors that we expect in our system anyway, right? Like you said, we're going to get shifts, and we're going to get rotation. So let's do that. I'm going to generate a new image from my marker image, but instead of just having the marker image like this, I'm going to paste it into a larger bitmap and randomly shift it around, and I'm going to try and rotate it. Now, actually, I'm not sure if the Python image library has a rotate function, but I hope so. Okay, good. Then we should be okay. So let's call that our image annotate, and I'm gonna turn this into a subroutine here. Oh, I can. This would be the output. So let's just finish the classifier. So here are the corners. That's the bitmap that I have here, right? Actually, destination, the actual Harris corner detector returns them as a list. So if I didn't want to threshold them, I could just return the list. But it's okay. This would be not the efficient way to do that. But okay, we'll just leave it like that for now. So we get the corners, and then I want to break it down into quadrants. So let's say that the count left, and we have width and height, no, height and width. Is the first two elements from image shape. So the count top left is p.count corners from 0 to height over 2, from 0 to height over 2, so let me just see what that returns. Image marker left. NumPy has no count. Some 28,844. if I change that here. True. Ah. Mm. See that where? Oh. Okay, then the numpy.where, I always forget exactly how that works. We have a condition. And the problem is that it doesn't take this one. as a single AND condition. It uses an OR, so I get like 4 values returned. So and then the axis should be equal to -1. No, not print. mp.all should be false, 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 lots of false. Okay, so that's better now. So I think this will be the corners. Corner check, and mp.sum. And here actually I can do this for everything. Corner check. Da, 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 da. $32 in the top left. Let's take all of them. So then I can just take the other ones, corner top right. Would be height over 2. 0 to height over 2. Corner bottom left. Height. Oh no. It will be this will be 0. This will be. Oh, and this is wrong. Should be height. This should be width here, of course. And then we have 0 height over 2, 0 width over 2. Then we have height over, no, width over 2. Then we have height over 2, 0 to width over 2, and height over 2 colon. And 0 to height over 2, no, height over 2 colon. 0 to width over 2, and then width over 2 to there. So that'd be top left, top right, bottom left, bottom right. Counter top left, counter top right, counter bottom left, counter bottom right, counter top left, counter top right, counter bottom left, counter bottom right. And then marker left, marker right, straight, oh count, not counter. And if I don't dilate it, then what happens? Then I have much smaller ones, of course. Okay, so left I have 6, 2, 4, 5. here I have 3555. And here I have 5523. Yes, because I don't do any. So here, these are actually 2 pixels that actually show up there. If I dilate them, I get a couple of more. If I wanted to have exactly one response there only, then I could do local maximum suppression, which means I go through the image and I see the corner response here, and then I check if I have 12, then I check any one of my neighbors. If one of them has a higher value, then I reset myself. So I don't count as a counter. So that means if you run that algorithm, then you're going to end up with only one maximum in the entire pixel space for one point. Then in that case, we will get exactly one pixel. But it doesn't really matter, like as long as we get some number that corresponds to the number of points here, that's fine. And I can even dilate them, then I get a couple of more points. That probably gives me a stronger response. But when we think about our problem from before that we discussed, then the issue is that we won't register correctly. So now here, these will be the correct, these would be the 3 classifiers. Right. 32, 12, 28, 33, 15, 30, 33, 30, 29, 31, 12, and 15. And you could sort of read off a binary code there, right? If you look at the numbers, then in this column, right, if I have a high number, then it's either left or right, otherwise it's straight. Because I didn't print them out, but I think it's left, right, or straight. Here, similarly, I have to have a low number there. Here, if this is a low number, and here we have a low number there for right and left. So that would work as a classifier problem.
Could you please break up your strategy here? Because I was working on my implementation, so I didn't catch what.
Yep, sure. Basically, I think we are the same up to here, right?
Okay, yes.
Yeah. So then I use a couple of NumPy tricks to simply extract the pixels and count the pixels that I want out of the bitmap. Right? Now the bitmap is ARGB.
Okay.
So the first thing I'm doing is I take the corners and I say I want all the pixels where that corner value is 000255, which is not good software engineering. We should probably set that as a constant, because that's just the value that I used here.
So what is this for value? This is not the color, right?
No, this is just how I paint the corner. So here, every pixel, I do the corner Harris detection,
Okay.
Harris corner detection. I dilate it, but the dilation is not really what we want to do. But it allows me to see the pixels better, right? Otherwise, it's kind of small here. These points would look very small. So we dilate them, and then I take that image, and anywhere where my Harris corner detector, where the response is 30% of the maximum or higher, right? Then I set it to this pixel. I can change this here to anything I want, but that pixel will be set correctly. And everything else is 0 in that image, right? So then here I go through the image and I say that I want the pixels where the corner matches that particular corner mark. But the problem is, if I just write that corners where the corner is this, then I actually get true, 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 false, because they're all 0, right? And I said 0, 0, 0, 255. So when it compares the pixel, it actually takes the pixel and compares it on each channel individually. So I get true, 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 false. If it's a corner pixel, then I get true, 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 true. So I say that for this to be counted, all of them have to be true, not just a single one. So basically this one here makes an AND over the red, over the ARGB values. This one doesn't AND over the ARGB values. Make sure that they're all true. And here I specify the axis as the last axis. So there's width. You can say everything in a column, or everything in a row, or everything in a pixel needs to be the same. And then that depends on what argument you set. Axis equals 2 or axis equal to -1 would be the same in this case. Then I just say the pixel has to match exactly 0, 0, 0, 255. Only then do I count it. And then here I just sum them up. So now here these are booleans, so they're either 0 or 1, whether they match or not, the pixels, then I just sum them up. In the top left corner, which is the corner from 0, 0 to height over 2, width over 2, right? So that would be the top left corner. The top right corner is the height is in the first half, 0 to height over 2, but the width now is from width over 2 to the end of the array. And similarly, I get the bottom left and the bottom right.
Sorry, what's axis equals -1 again?
Axis equals, if the NumPy functions, if you have NP sum is easier, I guess.
Yeah.
But np dot all is working the same way. So let's say a is equal to np dot a range 16 dot reshape 44. Actually, how many do I need? 3 times 16, 4, 4, 3. So now I get 3 pixels, and this would be the first row, second row, third row, and fourth row, right? So this is a tiny pix map now, tiny image. So now we can play around with this. So a dot sum mp.sum a would sum up all the numbers and then return one number, 1128, which is 0 plus 1 plus 2 plus 3 plus 4 plus 5, so on and so forth, right? If I go np.all, I now would check how many of those are not 0. Actually, let me just run it here. So sum is this. Yeah. Sum is this. All. Okay, so this actually returns a Boolean. It doesn't return the count, it returns a Boolean. So now it's false because not all of them are not 0. The first number is a 0. So now we can show the axis by specifying an axis parameter here. So when I say MP sum, then there's no axis. It doesn't add anything up. It'll just add it for each number as it comes along. Then I can go axis is equal to 1, axis is equal to 0. Now this will take the rows and add them all up together. So that gives me the 4 rows here.
Yeah.
And the pixel values, this one is everything in that first row added up together, right? And then I can go axis 2, which will, axis 1, which will give me the columns. So now it adds up the RGB values for each column, right? And 2 would be now it'll add up, it'll give us 60 numbers, and it'll add up the RGB values, right? So now here, this is the one that's the easiest to understand. This will be 0 plus 1 plus 2, which is the first 3 RGB values, so 3. Then 0, 1, 2, 3, 4, 5. So on and so forth. Now I just counted from the beginning, right? Minus 1 is the same just counting from the end. So this means sum up the individual pixels in each row. Sum up RGB in each pixel. So this gives us the same output, exactly the same as the previous one. And then you can actually, it's an extremely powerful function, and you should definitely learn how to use it properly, because not only is it extremely powerful, but it also is implemented in C++ with highly optimized vectorization. So anytime you need to do things like that on a 1024 by 1024 image, it would take it would be extremely slow if you write for y in range length of the image, or for y in range height, for x in range width. It would be an extremely slow process. This one runs blindingly fast. You probably would be hard pressed to beat this implementation yourself in C++. The NumPy version will run faster. So you can actually also do things like this, you can also set this to be a list. So you can say I want to sum up over row 0 and 2. And then that will give you the sum over all the pixels for each one of the columns. So now we sum up all the pixels, and then I said, did I say 0 or 1? 0. So 0 should be the columns. Ah, sorry, 0 is the rows. That should be the rows. And np.all is exactly the same, except with Boolean values.
Your strategy assumes that the markers are perfectly like.
This is not my strategy. This is his strategy.
Sorry. So I'm wondering, let's say we put the arrow white space, and the arrow is like right over here.
Yeah.
So that might.
That wouldn't work then, of course. That would be
We
problematic.
actually took some pictures with the arrows.
Oh, you did?
Yeah, let's see if it works.
And started with the run on the real pictures. And now the problem is different because now I think
So
we have to.
this is the image checking. So let's just say it's.
So this one is using the perspective distortion. This is very nice. This is what you
Robot perspective.
Yeah.
Yeah, so this is what this is.
So the first thing you would have to do would be to calibrate the camera of the robot so that you know the pan, the pitch angle. Right? If you know the pitch angle, you can actually take that image and convert it into a rectangular image. Right? So when I talk about camera calibration, the reason why we want to do camera calibration is in order to take a view like that and turn it into a rectangle view.
So it can just zoom into this instead of just.
We will look into that, but the idea is, yes, we know the outline.
I remember doing a project here, and I with a picture of some cards, playing cards on a table, and the image was perspective, and making from the image the rectangular.
Yeah.
So do you think
And
it's
what
possible?
project did you do that?
On YouTube, I was just something to learn OpenCV, and it was.
Okay. Because we do that quite a bit, because like I said, part of our research is to have the robots that do magic tricks. And we always look for cards and then produce to the cards. So if the problem is I didn't want to go through camera calibration in this course because I did it last term, and I thought that'd be a little bit boring, but I have what I think.
From this picture, that was taken from picture. So it's something like this. So from
Correct,
this
yes,
picture,
yeah.
taking this.
And that's what we would do with our markers as well. So registering the markers is a possibility. To actually do that, I'll just go through my.
This is that image.
Oh wait.
But this is not automated. Like this would individually pick the points. And our problem is that we don't know. Like we count every time.
Yeah.
But what I was thinking is, what if go back to the selections one?
Let me. Wanted to share this one first.
Maybe we can reason on like these white spaces, like the white spaces. Like, hey, I want
Slides,
to consider people who are not athletic. We need to yeah, this is matter. See, because we can clearly identify this region because it's just all that white. So maybe we can do something with this.
I think that we're just making it black.
So we're just
So that regardless of where the background, the robot is, he sees that. I'm guessing this one can protect clients because it has a database of different possible content. That might be so like you just feed the robot different images, left, right, and straight. And every time it goes to something it goes
for looking. Yeah. And then this
should
picture.
have mentioned that like that.
Yeah, alright.
Okay, so the first step in this application, one of the crucial ones will be camera calibration. Once you calibrate your camera, what that actually allows you to do then is, given a real world coordinate, you can match where that would appear in your image, right? So that's usually not the most interesting aspect of it, but that's, you can do that uniquely. So if I know that the point is at x, y, z coordinates 0.5, 0.7, 1.3, I can figure out, and I say that will appear on the image in pixel coordinate 290, 570, something like that, right? The other way is more interesting, right? Because in our case, we look at the marker, and then I get the pixel coordinate of the marker, and I want to figure out where that is in real-world coordinates with respect to the robot, right? So I want to map from image coordinates to real-world coordinates, from pixel coordinates to real-world coordinates. Doing that, however, doesn't work because I have an image. The image is only two-dimensional, so all I get is a line. Right? So we'll see how to deal with that. In lots of applications, that actually works fine. So the notebook that I have, for camera calibration, what we want to do is we want to find the relative pose between the camera and some object that we're looking at. So I want to be able to map the 3D world coordinates to do the image coordinates, and I want to map the image coordinates, but I need some additional information to 3D coordinates.
So we can assume that
Now,
sorry.
so now here would be an example, and I like that. This is a picture that I took of a Rubik's Cube. And then, okay, this is a three-dimensional object, and I just assign 3 planes to it, and the center points of these. Now, what actually happens mathematically is, first of all, the image is going to be that scene that we have here, there's going to be translation between the camera and the object, right? And there's going to be a rotation. So those are two sort of artifacts that we need to deal with. Now, they're actually pretty easy to deal with. Let's say I have a set of real world coordinates, x, y, z, and now I rotate those points by rotate around the z-axis. This is actually solved in computer graphics and robotics. This is solved using homogeneous coordinates. And basically, if we start slowly, do you know what homogeneous coordinates are? There's no W. There's a K usually, but it's not a quaternion. Quaternions usually use W's. But let's say I have a point, some point P here, that has coordinates x and y. Now I take the point and I rotate it around the origin, right, to a new point P dash, which now will have new coordinates x dash and y dash. So given x and y, I want to find some formula, some function that if I rotate the points by theta, x and y, then what will be x dash and y dash? Right? Now, the solution to that is actually the rotation matrix. You can Google it and look it up, but this one is actually pretty nice, so I think it's worthwhile to prove this from first principle. There's one, it's intellectual curiosity, and two, it is also important to understand why the equation that we end up with, why that particular rotation matrix actually looks the way that it does. Because sometimes you get a slightly different version by Googling. It depends on what your application actually is. So, to do that, I want to find x dash and y dash. As some function of theta and x and y. So how do I do that? I need to take the points and convert them into polar coordinates. So polar coordinates are polar coordinates represent a point not by the length along the axis, but by the distance from the origin and the angle with the x-axis. So call that alpha, right? So now if I take these points, x and y, if I take this point P, and convert it into polar coordinates, then what do I get? R is what? Arc inverse sine. No, I don't think that's how I would do it. What's the distance from here to there? Yeah. Quite, not quite right. Square root of x squared plus y squared, right? Correct? Yeah. What's alpha? Yeah, arc sine y over arc cos.
Arc tan y over x.
Yeah. In mathematics, that's how you would write it. Except I want to make sure my students never use A10 because if you write this, if you do this on a computer, you always want to use A10 too nowadays. Like, yeah. And the reason for that is because A10, A doesn't work for vertical lines, right? Because if x is 0, then this is undefined. A-tan 2 deals with vertical lines just fine. And even if it's not a vertical line, A-tan only returns the angle from 0 to 180, I believe. It doesn't give you the correct quadrant because once you divide, if x and y is positive, we're in the first quadrant, right? If x is negative, y is positive, we're in this quadrant. If x and y are both negative, we're in this quadrant here. And if x is positive and y is negative, we're in this quadrant. But if I do the division here, there's no way for a tan function to figure out if I'm in this quadrant or this quadrant, right? A tan 2 keeps track of all of this. And dealing with angles in a computer is already has enough what they would call foot guns. There's enough ways to introduce bugs into your program by not being carefully when you're dealing with angles or in particular differences between angles, because you may have a difference between two lines of 270 degrees, which is really the same as 90 degrees, right? So if you forget about A-tan, that's like the best thing you can do. Then you you'll never actually be able, you'll never be tempted to even use it. But I guess in math you would just write tan minus 1 the inverse. Yeah. But this is what we calculate on the computer. So this is what I have here, right? Okay, so how does that help me find x dash and y dash? Well, let's see if we convert our new point, right? After rotation, if I take that point and I convert it and I print out the polar coordinates, then what's r dash? Same, right? Not changed. And what's alpha dash? Correct, right? So then I could write the new coordinates in polar coordinates already, right? Now I could take the polar coordinates and convert them into Cartesian coordinates, then I get x dash is equal to,
R dash.
just take r
Or
instead of r dash,
R.
because r and r dash are the same. Yeah?
Cosine theta plus alpha. And then R is
Right, okay, good. So now I have my Cartesian coordinates already. But we can now simplify that equation even more. And in order to be able to do that, you would need to know the addition theorems for sine and cosine. Or, so you can either remember it, or you can actually prove it, which is a very nice proof. This is one of my favorite proofs. So here we have r, right? No, here we don't have r. Here we have r. Here I have theta. Here I have alpha. Right? Then, what I'm trying to find out is r multiplied by cosine theta plus alpha. Right? Now, in this particular figure, where would that be? This is r theta plus alpha, right? So it will be the cosine part here. This is what I'm interested in. Right? This is what I want to figure out, what I need to know. So how can I calculate this?
The left bottom one.
And it cannot really make the length 1, or it wouldn't actually do me any good I could scale the whole thing, but it wouldn't actually help me much. But the basic idea is that I can take this length, right, minus
I see. That
this length, right? So now if I can calculate this length and this length, then I can figure out what this length is, right? So what is this length?
the x-axis.
The x-axis, yeah, sure, but what is it?
R cosine theta cosine alpha.
Correct, and why? Let's have a look at this. What is this length here? Actually, I drew it badly. There should be both 90-degree angles here. Because we add them up together, right? This is r, then here I have r multiplied by cos theta, right? Because this is a right angle triangle, this is a hypotenuse, this will be the 90-degree angle.
So I cosine.
So this would be r cos theta. Then this part here, the green one, would be
R cosine.
no.
Sorry.
Cos theta multiplied by cos theta.
This would be this length here. Our hypotenuse is this length, right? Multiplied by cos alpha, right? How about this one? This length? So this angle here is alpha. This angle is 90 degrees. So this would be 90 minus alpha, right? This is 90, and the whole thing has to be add up to 180. So then this means this angle is alpha, right? So then that will be this distance here, right? Which is r sine theta. R sine theta. And then this part of that distance, so that would be r sine theta sine alpha. So that means that here I get r cos theta multiplied by cos alpha minus r sine theta sine alpha. And y dash is r, and then we can do the same thing. So y dash, I would be looking for this distance here, right? And you would use the same strategy. So here I get r cos theta sine alpha plus, and then this part here would be r sine theta cos alpha. And I think this is actually a very, very nice geometrical proof. Usually it's done using manipulation of the identities of sines, cosine squared alpha plus sine squared alpha, and you can manipulate the equations. But I like this proof a lot better. I think it's actually a very nice one. So now we have this. So now, what do I do?
So convert x, y now to
So r cos alpha is x, right? Yeah. And r sine alpha is y. So here, this would be y. This would be x, right? So that means x dash, y dash. So x dash I could now write as cos theta multiplied by x minus sine theta multiplied by y. Right? And y dash would be cos theta multiplied by y plus sine theta multiplied by x. Right? And now mathematicians, of course, they can't just leave equations alone. So a system of equations like that, they like to convert into matrices. So then I can write it as cos theta negative sine theta sine theta cos theta.
that's the rotation.
And that is the rotation matrix. Yes. Right? Now, I said, this is usually, if you Google for rotation matrix, this is what you get. Sometimes you get a different one, slightly different one. Sometimes the negative sign is here. And what's the difference? It could be the handedness of the coordinate system. More usually what happens is here we're rotating the point, right? If I rotate the coordinate system, then that's the same thing as rotating the point the other direction. So it depends on what you actually want to rotate. If you rotate the points, then this is the correct rotation matrix. If you rotate the coordinate system for whatever reason, then you would get the inverse angle there, which gives you the negative sign on the other. So don't just blindly Google things and then put them into your program and your robot goes haywire or something.
How to determine the original point that rotate you? Because
Right now we rotate around the origin, right? Then let's have a look. The other thing I want to do with my coordinates points is I may want to translate it, right? So if I translate it by tx, ty, then what will be my new coordinates, x dash and y dash? What's x dash here?
So x minus
No. I move from P to P dash here. So x dash will be x plus tx.
plus.
And y is y plus ty, right? So, okay, fine. Now, mathematicians like to have uniform representation. So they would like to represent this as a matrix as well. So we want to have, so what would be the matrix in order to do a translation? That would be nice, but actually it doesn't work because you can say, well, x, so okay, 1, right? Plus, but then I need to take like y, and I want tx there, so I need to have y multiplied. So it will be tx divided by y, right? And I multiplied it by y, I get tx. But that means that the matrix, I cannot just run all the points through. Here, I can have 100 points, right? I can all rotate them. Here, I would have to generate a new translation matrix every time for every value of y, which doesn't make sense, right? Because y here is a variable, but here I only want constants. So that's not cool. So in order to do that, I really need to add an additional value. And then I need to extend my coordinate system to add a constant 1 there, right? So this is called a homogeneous coordinate then. And really it was introduced simply to deal properly with simply to deal properly with translations. But it now has other uses as well. And in fact, homogeneous coordinates, the representation now is has been sort of extended, generalized. So here, instead of xy1, always 1, I can now write it as kx, ky, and k. So that means I can get a point, and I can add an arbitrary factor to it, right? That scales both the same. The x and y coordinate will be scaled the same. We'll see why that's important next class then, when we actually talk about the camera calibration. But what we have here is, now we have a rotation matrix, right? Which is very nice, and it has the minimum amount of information I actually want. Here I need to add this additional 1, and now I have a non-square matrix. So that's also something that that mathematicians don't really like. So instead, we take it and convert it into a 3 by 3 matrix. So the rotation matrix will be cosine theta, negative sine theta, 0, sine theta, cos theta, 0, 0, 0, 1. And the translation matrix would be 1, 0, tx, 0, 1, ty, 0, 0, 1. Right? And that gives us now a generalized representation for any translation, any rotation. Right? It can also do a couple of other things. But first of all, let's say, what happens if I don't want to rotate around the origin? What happens if I want to rotate around some point Q here? Correct. So we translate the origin to Q, or we translate Q to the origin. Right? We bring Q to the origin, then we rotate around the origin, and then we translate the whole thing back. Okay? Now, since these are homogeneous transformation matrices, that means what actually will happen is that I start with my points x, y, 1. And now, first, I want to do the translation from minus q. Will be negative qx, negative qy, because I need to translate q to the origin. Then I do the rotation by theta, and then I have to translate everything back. And the important thing is I can combine these homogeneous transformations easily, but I have to make sure that I'm using the right side multiplication. So matrix multiplication is not commutative. So A times B is not equal to B times A when we're dealing with matrices, right? So here I have to keep multiplying on the left-hand side, because first I translate, then I rotate, then I translate it back. So that's how we do rotation around the origin. Not around the origin, around an arbitrary point. I need to take the arbitrary point, move it to the origin, rotate, then I translate it back to where the point is. And using this representation, we can do a couple of other things instead of just rotation and translation. We can also do what happens if I have two 0.5 as my rotation, as my transformation matrix. So that will be multiplied my coordinates, right? So then the new x dash will be 2 times x, right? And y will be 0.5 times y. So that means that whatever the previous x coordinate was, it will now be twice as big. So that means we're zooming in the x direction. We enlarge the x direction. And the y direction will be half that, so it'll be squashed. So we can do Sx, Sy here in order to do scaling. So that's another what's called affine transformation, and that's what we can represent as a homogeneous transformation matrix as well. And then there's the last one, which looks like this: 1 k x 0 0 k y 1 0 0 0 1. Now, what kind of operation is this? This one here, let's say 1, 0.5, and here at least this one is 0. Then I get xy1, right? So here I would get, actually this would be k1. So here I would get x plus 0.5 times y, right? And y would be unchanged, 0, 1, 0, and 1. So x increases by half the y, which gives you a skew operation. It will be, if it's a rectangle, if I have a rectangle and I rotate it, right, then I end up with a rotated rectangle. Fine. If I take the rectangle and skew it, then I end up with a thing like this. So here, this will be a skewing on y, right? Because as I go up y, I add more with 2x. So translation, rotation, scaling, and skewing are the affine transformation that we can, and they can all be represented using homogeneous transformation matrices. In 2D, we end up with a 3 by 3 matrix, right? In 3D, we end up with the same thing applies. I can do the same thing, except I will end up with a 4 by 4 matrix. And that's why when you look at computer vision and computer graphics, the most primitive, up to now, the most primitive operation is to multiply it by a transformation matrix, which is a 4 by 4 matrix. That's why all Photoshop, Blender, all the CAD programs have 4 by 4 matrix operations hardwired in, because that's like the bread and butter. That's how you are able to plot something on the screen, points. Okay. So then next time we can look at camera calibration, because this now I can take a camera like here, right? And I can now rotate that camera and translate it anywhere in the world. But I will not end up with the picture that you would see with the human eye. Because the one thing that we haven't modeled yet, or that we haven't been able to, that we wouldn't be able to represent as a 3x3 matrix here, would be the perspective distortion. The fact that things that are close to the camera are bigger than things that are further away from the camera. That's the perspective distortion, and we'll talk about that next class. So all the students, if you don't have a group yet with the German students, then today is your last chance. Make sure that you are either here in class or online at 2 o'clock, so that we can arrange student groups. Who still doesn't have a group? German group? German students? Okay, how come you don't have any? Previous Mondays, you were sleeping or what? Okay. You still need to arrange being able to do the hackathon with the Germans. So make sure that you have a group by this afternoon, and you just got here. Okay, good. Then that's it. How come you cannot communicate?